Imagine you're suffering from a splitting headache in the year 1850. Your best remedy is a bitter, stomach-churning tea made from willow bark. We knew the active ingredient was salicylic acid, but extracting it from plants was slow, expensive, and frankly, messy. But then, Herman Kolbe discovered something that felt like modern alchemy. He could breath carbon dioxide into a byproduct of coal tar, phenol, and turn it into that very same medicine. This is the Kolbe-Schmidt reaction, and it's arguably the birth of the modern pharmaceutical industry. To understand how this works, let's look at our starting material, phenol. At first glance, phenol looks like a standard benzene ring with an OH group attached. But notice that oxygen atom. It's hoarding electrons, and it's not very happy about sharing them with a weak molecule like carbon dioxide. If we want a reaction to happen, we need to make this ring much more hungry for a bond. Watch what happens when we introduce a strong base, like sodium hydroxide. The base snatches the hydrogen from the oxygen, leaving us with a phenoxide ion. Now, look at the charge. That negative sign on the oxygen isn't just sitting still. Through resonance, it pushes that electron density into the ring itself. Notice how the ortho and para positions suddenly light up with negative charge? The ring is now primed and ready to attack. Now, let's bring in our second player, carbon dioxide. Normally, CO2 is incredibly stable. It's the final product of combustion after all. It doesn't want to react with anything. But look closely at its structure. Those two oxygen atoms are pulling electron density away from the central carbon, leaving it with a partial positive charge. Here is the key insight. Even though CO2 is a weak electrophile, our phenoxide ring is now such a powerful nucleophile that it can force a bond. As we visualize this attack, notice where the CO2 goes. It doesn't just land anywhere. It targets the carbon right next to the oxygen, the ortho position. But why? This is where the sodium ion, the spectator we usually ignore, comes into play. Picture the sodium ion acting like a chemical bridge or a matchmaker, holding both the phenoxide oxygen and the incoming CO2 in exactly the right orientation. This chelation effect is the secret reason why we get salicylic acid specifically. Once that bond forms, the ring momentarily loses its aromaticity, its structural soul, if you will. But nature loves stability. A quick shuffle of protons occurs, the ring regains its aromatic circle, and after we add a little acid at the end to neutralize the charge, we are left with salicylic acid. It's a beautiful piece of molecular engineering. We took a simple waste product, used high pressure to force a gas into a liquid, and created the precursor to aspirin. Next time you look at a bottle of pain relievers, think about this. You aren't just looking at medicine. You're looking at a 170-year-old trick of thermodynamics, a way of capturing a simple breath of CO2 and locking it into a shape that can quiet the pain in the human brain.